Hey guys, so in today's video, we're going to be talking about the driving forces of chemical reactions and net ionic equations. So to start off, let's talk about the four major driving forces of reactions. Now, a reaction's driving force is just something that causes it to move forward. There are four major driving forces I have listed here. The reasons are either water forms, a precipitate forms, a covalent compound forms, or gas forms. Let me show you examples of each and every one of these. For our first example, you can see that sulfuric acid is reacting with potassium hydroxide to form potassium bisulfate and water. Because water is forming here, and because water isn't an acid or base either, in an acid-base reaction, the production of water will drive the reaction to completion. Now, the second example is the formation of a precipitate. In here, we have zinc chloride reacting with sodium carbonate to produce zinc carbonate and sodium chloride. Now, the sodium chloride stays in solution, but because the zinc carbonate is going to fall out, it's going to keep moving so that we can keep replenishing the zinc carbonate. It's kind of like equilibrium. Now here, a covalent compound refers to a compound that doesn't ionize, or at least doesn't ionize too much. Usually, it's a weak acid that forms, like say organic acids. For example, magnesium acetate reacts with sulfuric acid to form magnesium sulfate and acetic acid. Now, the driving force is that acetic acid doesn't ionize too much, right? It's a weak acid, so logically, it's not going to ionize too much in solution. So that means that more protons and acetate ions will bind to form acetic acid, and therefore that's going to drive the reaction forward to this side. And lastly, the formation of gas. Here I have ammonium perchlorate reacting with sodium hydroxide to produce ammonia gas, water, and sodium perchlorate. Now an added driving force is the formation of water, but the ammonia gas itself will be more than enough to drive the reaction to completion. This is because if a gas is produced in the reaction, then the gas will just get out of the container, and because of that, the reaction will keep trying to replenish more of the gas. And then it will eventually consume all the reactants, and we'll be left with their products, water, sodium perchlorate, and ammonia. Now, as I've written here, sometimes one driving force can be more powerful than another force, and therefore push the reaction to one side. Here I have copper 2 oxide reacting with sulfuric acid to make copper 2 sulfate and water. Now, as you can see, you may think that the reaction wants to go this way because copper oxide is a solid, and therefore it will want to go push that way. Well, because water is produced here as well, and because the formation of water is arguably one of the strongest driving forces, it would prefer to go to the side with copper sulfate and water. Now let's start talking about net ionic equations. So the basic idea of a net ionic equation is just any old ionic equation, except we're going to simplify things so we get rid of anything that doesn't really react. For example, the overall reaction here is the reaction of triethylamine hydrochloride with sodium hydroxide, which forms water, sodium chloride, and triethylamine. The formation of a covalent compound in water will drive the reaction forward. However, you can see that because sodium chloride will dissociate into sodium ions and chloride ions, and because this guy will just turn to sodium ions and hydroxide ions, and this guy will turn to triethylammonium ions and chloride. And because the chloride is still going to be in solution, and the sodium ion, they're still going to be floating around. So, because of that, we're just going to take them out. They're not going to be doing anything in the reaction. They're just hanging around looking at what's happening. So the net ionic equation is the reaction of triethylammonium ions and hydroxide to form water and triethylamine. Now, water, gases, precipitates, and covalent compounds are represented as molecules because, after all, they can't ionize or anything. So Now what happens if a double displacement reaction occurs except both of the compounds that might form are soluble? Well, first we gotta split up our compounds into its constituent ions. That's the basic step to every single net ionic equation. So we have aluminum, chloride, sodium, and sulfate ions in solution. Well, if you look at that, then they're just gonna stay in solution. Nothing will really precipitate. Sodium chloride is soluble, aluminum sulfate is soluble, these two are soluble, and therefore we won't have any ionic equation because, well, there's pretty much no reaction going on. Now let's try balancing an ionic equations that actually do have a reaction. Here I put the reaction of cupric chloride with sodium sulfide. The reaction will generate sodium chloride and copper 2 sulfide, which will precipitate and therefore become the driving force of our reaction. Well, let's also put in our ions. So we have sodium, sulfide, copper, and chloride ions on the reactant side, sodium and chloride on the product side, and copper 2 sulfide on the product side as well. Well, it's just like your Algebra 1 class you got learned in junior high or high school. You see, there are two sodiums here, two chlorides here, and two sodiums here, and two chlorides here, right? Well, because we have two sodium ions there, two sodium ions there, it doesn't really mean that the sodium is reacting or doing anything. So why not just get rid of it? So we need to cancel out the sodiums and chlorides, and we're eventually left with copper 2 plus ions binding with sulfide to form copper 2 sulfide. Which actually makes very much sense. Copper 2 sulfide, and it makes copper 2 sulfide. Honestly though, it's kind of simpler now that the excess ions are out of the way. Now let's look at another net ionic equation, this time with the formation of gas. This one is a reaction of sulfuric acid with table salt to produce hydrogen chloride gas, which is, well, hydrochloric acid if it dissolved in water, and sodium sulfate as a side product. Well, let's look at how we're going to simplify it. Okay, so we broke it up into our ions, right? Now you may have already noticed that we have two sodiums here, two sodiums on there, and because we have these two ions on both sides of the equation, we won't really need them anymore. Now you may wonder why I split up sulfuric acid, and that's because in a net ionic equation, strong acids and strong bases will fully dissociate, and therefore we would just consider them as hydrogen ions and sulfate ions rather than just the molecule itself. This isn't true for weak acids or weak bases though, because they ionize only a very tiny amount, so small that you can practically ignore it. However, strong acids like this guy will dissociate completely. Now you may wonder, wait, hydrochloric acid is a very strong acid as well. Why aren't we splitting that guy apart? Well, that's because here, the hydrogen chloride is actually present as a gas, and therefore it's going to go away. And because it's a gas, we're still going to consider it as a whole molecule, even though it's a strong acid. So if you simplify, the sulfate and sodiums cancel, and we get two hydrogen ions and two chloride, making 2 hydrochloric acid. Well, we can make it simpler. We divide both sides by 2, and then you get H plus Cl minus equals HCl gas. Okay, so let's just look at a quick chart of gases. Now, formula and the gas form and the aqueous forms are listed here. Now, as a side note, for ammonia, ammonium hydroxide doesn't actually exist. They just call it that when the ammonia solution is concentrated. That's just a nickname that isn't exactly true. So it's probably better to just call it NH3, AQ in parentheses, or you can just add an H2O by its side. Either way, it'll still work. Just, I don't really recommend ammonium hydroxide all that much. So take a quick look at this and let's move on. So did you memorize it yet? Pause the video if you want to keep memorizing or take a screenshot. I'll just move on ahead right now. Okay, so here we have a single displacement reaction this time, not double, single. So this time we're only going to split tin 2 chloride into its constituent ions, right? This is all gone into your head. We split them into the ions. We already got used to it. So we split the tin 2 chloride and zinc chloride on the reactant side and product sides to form zinc metal, tin 2 chloride, and all this as our products. Well, you may have already noticed 2 chlorides here, 2 chlorides there, we let it cancel, and you can already see the net ionic equation. Zinc reacts with aqueous tin 2 plus ions to make zinc ions and tin metal. Now, what if we do this? Now, some metals, like say potassium or sodium, are reactive enough to react with water. If that's the case, then, and because hydrogen is produced, that'll be the driving force of the reaction. For that case, the net ionic equation will just be potassium with water, forming potassium ions, hydroxide ions, and hydrogen. Well, it's similar for a less active metal reacting with an acid. You see, the less active a metal really becomes, the less willing it is to give away its electrons. The more active metals will be just, oh, I have my electrons, anybody, please, like that. But the less active metals will not be as convincing to give up its electrons. So we have nickel metal reacting with sulfuric acid to form nickel sulfate and hydrogen gas. Now you may have already noticed, hydrogen is a gas, and therefore it'll be a driving force of the reaction. Again, we split up our sulfuric acid into its ions. Totally makes sense, we already know. Now you see, one sulfate here, one sulfate there, these guys cancel. And we're eventually left to very simple nickel metal, hydrogen ions forms nickel ions and hydrogen gas. Now, a very similar reaction can occur with nonmetals as well. Well, why is that? Well, that's because, like the metals who give away their electrons, the nonmetals want to earn their electrons. And because of that, we also have a reactivity scale just for nonmetals. So the more reactive nonmetal will want to gain electrons, while the less active nonmetal won't be really into electrons all that much. Here's a good example. We have chlorine gas reacting with potassium iodide to form potassium chloride and iodine. Chlorine is a very aggressive oxidant, whereas iodine, not so much. So again, we split up into our ions, and 2 potassium here, 2 potassium there, cross them out. And you can already see chlorine and iodide forms chloride and iodine. Now, here's a quick chart of the reactivity scales I made. Now, this will be very important later on, but right now I just put some simple details. Later, we're going to talk more about it once we get into redox and standard reduction potentials, but that's not our concern yet. So as you can see, the most active metals, cesium, rubidium, potassium, sodium, lithium, barium, strontium, and calcium, are apparently so reactive that they're willing to react with water. Even the cold water you can find in your tap water or anything, it'll react to form their respective hydroxides and hydrogen gas. The next ones, magnesium, beryllium, and aluminum, will react with water, but not that fast. Also, they'll react extremely vigorously if contacted with acid. The next ones, titanium, magnesium, chromium, iron, cobalt, cadmium, nickel, tin, lead, will react with acid, but as you go down the scale this way, it's going to be less willing. Also, titanium, unlike what some of you might thought, titanium is very active and it's very willing to react with acids to form titanium salts. And finally, antimony, bismuth, copper, mercury, silver, gold, and platinum aren't actually going to react with too many acids. It will react with very strong oxidizing acids like say nitric acid, but with normal acids like hydrochloric or sulfuric acid, it won't do too much. Here's the scale I made for nonmetals. Fluorine is actually so aggressive that it can set almost everything on fire. almost everything, but still. Chlorine is a very powerful oxidant. Even though it's second place, it's still very, very powerful. So it can oxidize many metals into their very high oxidation states. For instance, with platinum, at red heat, it can react with it. Now, bromine isn't that strong. I mean, as you go down the periodic table, on the halogen side of the table, then the elements will be less willing to gain electrons and therefore become weaker oxidants. So bromine, I'd say it's a decent oxidant, not too strong, not too weak, and it will react with many metals. Iodine is rather weak of an oxidant given its very low standard reduction potential. In fact, it'll even get oxidized by copper 2 plus ions. And astatine, I put not tested because astatine is just so unstable that it's just gonna decay into some other element before we even start reacting it. So that was AP Chemistry Part 7, and we learned about how to produce net ionic equations and what the driving forces of chemical reactions are. Thanks for watching, and see you in our next AP Chemistry videos. Bye!